Good morning, students. Okay, we have started with work and energy, where we have discussed what work is and what energy is, and we have ended up at work energy theorem. Okay, so today we are going to discuss starting from the potential energy. Okay, last time I have said we have two: mechanical energy, kinetic energy, and potential energy. So we have discussed about the kinetic energy. So they will discuss about the potential energy. So what the potential energy is? Okay, so when we talk of the potential energy, we define it as the energy stored by an object due to its possession. So it means the potential energy, it's the energy relates to the possession. Okay, so there are many kinds of potential energy, but you only discuss two. Okay, so you only talk about the gravitational potential energy and the elastic or string potential energy. Okay, so gravitational potential energy, as I said, potential energy itself, it's the energy stored by the body due to its possession. So the energy must be given to any object to raise to a certain height. Okay, so if you have an object which is this possession, okay, in order for this object to be raised to a certain height, then the energy must be given to this object in order for it to rise. As we said that in order for it to do work, it requires energy. Okay, so in order for this object to be released from this height, okay, say height 1 to this height, then there needs to be energy supplied to that object. Okay, so the energy released by an object when it is lowered, like if you're taking from a height and you are actually releasing that object from a certain height coming down, okay, so then they need to release the energy. Okay, the gravitational potential energy represent, okay, the capacity of an object to do work, okay, by virtue of its possession. So the gravitational potential, as I've said, the energy is the ability to do work, and in order for the object to be released from or to be raised or released from a certain height, then you need to do work. As I've said, work in physics, we define it relating to the force, and there should be a motion for it to have a work done. Okay, so suppose an example here, suppose you are lifting up a particle from one position to another position. Okay, so it's from a height 1 to height 2, and that object is not accelerating. Okay, so then in order for you to lift up that object of that mass, then you apply an upward force. Okay, so remember that because you are pulling it up or you are either pulling it down, then you apply a force, upward force, which is equal to what? It is equal to the height. Remember, this object is not accelerating, so it means at every height this object has the same energy. It's not accelerating, so it's moving up with a constant velocity. So remember, we defined and we say that the work done is equal to the force times the displacement cos of the angle. Okay, now if we want to calculate what is the work done by the weight, as the force, as you are lifting up this object, from a position height 1 to the height 2. Okay, so you want, okay, so as you are lifting up this object from this position to that position, then what is the work done? Remember, when it's going up, I always say there's a weight associated with an object because this object has a mass. Okay, so what is the work done due to the gravitational force, which is equals to weight? Okay, this is the displacement as it goes up. Okay, so from that point to that point, that is the displacement of that object. Okay, so remember we define our force, our work is equals to the force times the displacement times the angle, cosine of the angle. So when we look up between the weight and a displacement, so we'll see we see that the weight and displacement are in the opposite directions. So the weight goes up, down, while the displacement is going up. So we have that the weight and the displacements are in the opposite direction. So if consider this is our 90 degrees, so it means the displacement is at 180 degree. Okay, so if we plug in here, so then the force that it does is due to that force, which is the weight, times the displacement times the cosine of 180. Okay, the cosine of 180 degree is negative. So we see that the weight here, so it's the force, it's a negative force times the distance. Okay, and we calculate our weight as what? As the mass times the gravitational acceleration times the displacement. What is our displacement? This object, it's displacing between y2 and y1. Okay, so what do we see here? So we see that the work done due to the gravitational force is equals to the minus the mass of an object times the gravitational acceleration times the what? Times the displacement. So what we see is that in order for this work to be done, then it requires an energy which is in the form of mass times the gravitational acceleration times the displacement. Let me say just y. So what is this energy? So we define this energy as the potential energy. So therefore, the potential energy or the gravitational potential energy is given as the mass times the gravitational acceleration times the displacement or the height between like from where it is moved from to where it is it ended. So it's like the between the two between starting from the reference point to where it is going. Okay, so if we say this y is just measured from our reference point, where did we start? And the most of the time, most of the cases, we say that it's due to the ground. So we set our reference level to be the ground. So this value is not fixed, it depends. Okay, so that means this the y, the displacement between the two depends on your reference level. Where did it start? So it's not fixed always. Okay, so this is just what we were talking. So where that height, here we have in forms of the height, it's simply the height above the level. So as I said, it's just the distance between your reference level and the ending point. Okay, so as the reference level is not fixed, it can be chosen at the different levels in different problems. Depends on what you have. In most of the cases, as I've said, we choose the ground to be the reference level. So, and if you choose the ground to be the reference level, then we say that our y, the starting point is equals to 0. Okay, so as you see on that equation, then we have that the potential energy depends on the height and on the weight. Okay, so we'll see that. So when you are calculating the potential energy, what is important for us, we only look at the vertical height. That is what is important when it comes to the gravitational acceleration. I mean gravitational potential energy, regardless of how did it goes, whether goes up in, whether that object goes up from an incline, going up like that, going up like this. What is important, what matters is the height, the vertical height between that 2 points, not the path. Okay, so it means the gravitational acceleration is independent of the path of the object. Okay, so as you can see, we say that we calculate our gravitational potential energy with work done is equals to that value there. Okay, so this is what we had up on this, where we are saying that the work done by the gravitational force is equals to the minus of the mass times the gravitational acceleration, and times the change in position. Okay, this minus is not even surprising to us, because we have said already that the work can be positive, can be negative, and can be 0. We say that if the displacement and the work are parallel to one another, if they are going in the same direction, then you have a work which is positive. If they are going in the opposite directions, as we say, then we say that we have the work which is negative. And if the force and the displacement are perpendicular to one another, then there is no work done, so we have the work which is equals to 0. So this one, especially if you look up on the work done due to the gravitational acceleration, due to the gravitational force, it's not surprising to us, because we have a work with we can see that our work and the force and the gravitational acceleration is, the displacement and the weight is opposites to one another. Okay, so back to this equation here. So we said that we have a work done which is equals to minus the weight, okay, times the difference, the displacement, minus the y1. Okay, where we say that the weight, it's minus mg times y2 minus y1. So if you will multiply out this equation, then we see that we have a minus the mass of the object times the gravitational acceleration times what? Times the y2, which is the distance, minus the y mass times the gravitational acceleration times the y1. What do we see? Okay, let me just take the minus out. Then we will say that what is this? We say that we define our potential energy as equals to what? Mass times the gravitational acceleration times the height. So what is this? So we see that this one is the gravitational, it's the potential energy at where? At point 2 minus the what? The gravitational potential energy 8.1. So what do we have? We see that this one is equals to minus change in the potential energy. So what does this give us? It says that the work done due to the gravitational force, it equals to the minus in the change of the potential energy. Okay, so it means that the work done due to the force between the 2 points, okay, is equal to the minus of the potential, or the change in the potential energy. So this is what we have there. Okay, so as the object moves from that one point to another point between the 2 points, it's equal to the negative of the change in the potential energies. Okay, so it means in general, because if we calculate for both, so we have that in general, the change in potential energy associated with a particular force. This is very important. So with a particular force, it's equal to the negative work done by that force if the object moves from one point to another point. Okay, so what does it say? You can define this, maybe it's so confusing. What does it say? It says that, remember in Newton's third law, we are saying that for every force, there is a reaction force. Okay, so we define that the change in potential energy as the work is required for any extra force to move an object between the 2 points. Okay, so that change in the potential energy between the 2 points. Okay, so because if we look up on these two, if we look up into this, if there is an extra force, okay, if this is an object moved to that position, remember, as I said, it requires a force, the upward force. Okay, and here they say a weight force which is acting. So you see that between this force is reacting to that force. So if you look up, the work done due to the gravitational force is equal to the minus the potential energy, while the work done due to this force is equals to the positive potential energy. So, and this is what it's saying, for every force, okay, every force, for every particular force, the work done, okay, so the change in the potential energy is equal to the negative of the work done of that particular force. Or you can just put it in another way, that the change in position, because of the Newton's third law, the change in position, the change in the potential energy as the object moves from one point to another without accelerating. Okay, this means that object is moving with a constant acceleration at every point. Then the work done is equals to the change in potential energy. Okay, so, and this is what is important there. Okay, we have an example here. It says a box has a mass equals to 5.8. The box is lifted from the garage floor and placed on a shelf. If the box gains 145 joules of potential energy, how higher is the shelf? Yeah, I even put the answer for you there, but let's work it out so you can see how it is worked out. So it says we have an a car which is lifted up from the garage floor. Okay, so it means it's just from the ground. This one is just to 0. Okay, so it's lifted up from this to a height. Okay, so the potential energy as that object is here, the potential energy at that point is equals to 145 joules. Now, how higher did that can move from that to there? So we say that the potential energy equals to the mass times the gravitational acceleration times the height. Okay, so we are given that the mass of that box is 5.8. Okay, so we are given that the mass of that object is equals to of the box is equals to 5.8 kilogram. Okay, so by using make use of it, because we are already given the potential energy, so on place of the potential energy is what we are putting up here. So it means that the potential, our height is equals to the potential energy at that position divided by what? Divided by the mass times the gravitational acceleration. Okay, we know what our potential energy is. We know what our mass is. And we know what our gravitational acceleration is. By plugging in there, we should get the answer. We know all these values. So it's simply asking you to find what the height is. The second equation here, it's saying a 800-gram ball is pulled up a slope as shown in the diagram. Okay, so we pull up a ball from this position. It means it's pulled up in an incline, as you can see. Okay, calculate what is the potential energy did this object this ball gain as it gets up at this point. Okay, if you look up on this one, you see that the distance it traveled is this one, but not this one. But I have said the potential energy only depends on the vertical height, not on the path. So the distance that we have to consider when you are calculating, because this hill or whatsoever is this one has a height which is equals to 20 centimeters, and this is the vertical height which is important to us, not this one. Okay, so the force, it's due to the height, the work or the potential energy is due to this height, so we simply use that height there. So we have, and the object is in that. Okay, and we are given that height. So, and this is the height that we have to consider. As I said, it only depends on the vertical height, not on the path. Okay, so it means that the potential energy at this point, potential energy there is equal to the mass times the gravitational acceleration times the vertical height. Please, you should always make use of the SI unit. So we have to divide the 800 gram by 1000. It's always very, very important that you always have to make use of the SI units when you are doing any calculations. Okay, so times 9.8 times the height of 20 centimeter, which we have to divide and convert this to meters. Okay, so we get all that. We know that. Our mass is 800 over 1,000 because the mass it is given is what it's in grams, and our distance or the vertical height is equals to the 20 centimeter, which we have to convert to meters. You do a calculations, should be able to get what the potential energy is at that height. Okay, I said we have two types of we're gonna discuss two types of potential energy. So we have a potential energy due to the strings or the elastic potential energy. Okay, so this one, elastic potential energy, is we relate this one to the strings or any elastic object. Okay, so the string or any elastic object has the potential energy. Okay, so the tendency to do work when either compressed or stretched. Okay, so the force that attempts to restore a stretched or a complex string to its original state is called the elastic force. You know, remember you have done a spring, the harmonic motion. So this is why it is important now. Okay, so if this is our spring, this is the unstretched spring. Okay, then let me say you stretch up this object, that string to that position. Okay, so you see that as you pull, okay, as you pull up, if this is my stretch, as you pull up on this, as you are pulling up your string on this, you are applying a force. Okay, so the force which is opposing that force, the force which is trying to take that to release or to bring it back to its original string. Okay, and we can denote it as the string force. That force is called restoring or restoration force. This force is attempting to bring this object back to its original state. Okay, and by Hooke's law, we say that that force is equals to a minus the string constant times the what? Times the x. What is this x? The x is the displacement it made, whether it is compressed or stretched. Okay, as this distance, like if it is stretched, the distance from its original state. Okay, so the distance it's stretched with from that to that is what is that x. It is displacement. So it's the this force is equal to the minus, but the string constant times the x, and the magnitude of that force. Remember, every force is a vector. The magnitude of that force is equals to, please log in once we finish so we can try to finish up this part. Okay, is the constant spring constant times the string. So this is the magnitude of that. Okay, so and that force is measured in newtons, and the spring constant is measured in newton per meter. Okay, so this is just what I was saying. The magnitude of that elastic force or the restoring force is equal to the k spring constant times the displacement. Okay, so this k, it measures the stiffness of the spring. Okay, like the stiffness, it's just how higher, like how is it bounded. Does it requires more energy for it to be complex? Does it require more energy for it to be stretched or what? Okay, so this is the force it gets. Okay, so now what is the work done by the spring? If you want to calculate what the work done by the spring is, okay, by that spring force, we make use of the graph. Okay, so we know what is the force, and remember that force, it keeps on increasing the more you apply. Okay, so it keeps on increasing until it stands, it's no more going, because when it reaches that the maximum force, that force will stand. Okay, so if that is the maximum spring of that force, then that is the displacement it causes. Then the area, if we calculate what the area under the graph is, we get that is equal to the half times the spring constant times the displacement it made squared. Okay, so we get that this is equals to that one there. Okay, so what is the potential energy of the spring? Remember we said that the work and potential energy are one thing. Okay, so the potential energy of the elastic object is equals to the half kx squared. So it means that this point only depends on the starting, the initial point where it starts, and the final point, and not on the path. So this one, as we said, that the potential energies only depends. So this is also the same here. So both the potential energy only depends on the distances it travels. I mean the starting point and the ending point. Okay, either on the vertical, or like now for this one, it's the x is in the x direction. So it only depends from the starting point and the last point. It does not depend how did it travels, whether it goes in a curve or it goes in the what matters is only 2 points only. Okay, before I go on, I need to know if there are questions. You have questions?
Ms. Nambinga,
Yes.
you said the K. X I know is a displacement. What is the K again? You said it measures what?
The K is the spring constant, and it measures the stiffness of the spring.
Yes, the stiffness. Thank you.
Miss,
Mm-hmm.
can you please go back to where there's a triangle?
Where there is?
The last example. In potential energy.
The gravitational potential energy. Mm-hmm.
Yeah. Okay. At first, we calculated. Okay. At first, we calculated what?
Which
The first example.
the
now.
first example. The first example the first example we are calculating the displacement, the distance. How higher is the fall? So the first example we are asked to find the distance.
Oh, and then for the second is now the potential.
Yes. The second example is asking us to calculate what is the potential energy.
All right.
No more questions? Okay.
We can continue.
Okay, we can continue to in the time remaining, but so please log in again once we are logged out. They are saying we only have 4 minutes. Okay, we move on to the conservative forces and non-conservative forces. What do we mean when we refer to the conservative forces and non-conservative forces? Okay, so the conservative forces, we refer to the work done, okay, which is independent of the path. Okay, so when it comes to the conservative forces, so we look at the forces that does work that only depends on the only depends on the 2 points, only depends on the initial points and the final points. So it means these forces they are independent of the path that the object move. And in this force, we are mostly it's where we refer to the potential energies. Okay, and what about the non-conservative forces? So the non-conservative forces are the forces that do work, and these ones they depend on the path. Okay, like if an object moves from a vertical, let me say it moves in the vertical or in an incline, so you know there's a forces that are occupy there. So it means these forces does not depend on the starting point and the final point. It depends on how did this object move. Okay, so it depends on their path. So these are the friction for the non-conservative forces. So we have examples here. So mostly we have the gravitational forces, as I've said. So the conservative forces actually just include the potential energy. Okay, you know the elastic forces is a potential energy, the buoyant force is a potential energy, the elastic force is the potential energy, gravitational is a potential energy. So in one way, in other words, the conservative forces are actually all the potential energies are conservative forces. While in the non-conservative forces, these are the friction force, the air resistance, the tension, the normal force, the pull, okay, the pull and the push. Remember, if you are pulling, you are applying a force that is an external force. So any external forces, if you have any external forces, then those forces are non-conservative force. Okay, so the non-conservative forces are also called the dispersive forces. Okay, as they disperse, or I can say they they change. Okay, they convert from one form to another form. Okay, so the potential energy can be defined only for the conservative forces, as I've said. Okay, so if we come into that, then remember we had the work energy principle. At first, when you're only looking at the work and energy, where we only had the kinetic energy itself. Now we are going to extend that potential energy and include the potential energy. Okay, so suppose that we have several forces acting on the object. Okay, and these forces on that object, some of these forces are conservative and some of the forces are non-conservative. Okay, so we say that the conservative force are all the potential energy. Okay, this is what we defined. So this is what we said. Okay, so we said that the conservative forces, it's equals to the what? The potential energies.